Hello. In this third video on section 10.3, we're actually going to get to defining what a Fourier series is. So remember what motivated this. In the last section, we found it useful. We found it that we could really easily solve the heat equation if we were working with functions that were like sums of sine functions. And so we're now thinking about when we can represent a function as a sum of sines. So let's think about this infinite series. We're just going to write this down. A0 over 2 plus a sum from n equals 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L. Now we don't have a b0 term because then we would have sine of 0 pi x over L, and that's just 0. And then the a0 over 2 is a convenience that will become apparent later, but it really doesn't much matter. So now if this series converged, if this converges, then the function that it converges to sort of point-wise, so for any x, f of x would be whatever value this series converges to. It would converge to a function which is periodic with period 2L. And the reason for that is that each of the sine and cosine functions have period 2L, and so the sum of all of those would also be periodic. So let's assume, for now, that this thing does converge. So it equals some function f of x. And so now we want to think about what would the a_n's and b_n look like. Whoops. Basically what we're doing is saying if we could write an expression like this, how would we find it for a given f of x? You know, how would we compute this trig series? Just like when we tried to compute a Taylor series, we know how to compute the coefficients. They're, the derivatives of the function over the factorial. And so once we know how to compute these coefficients, the an and bn, then we can worry about when it converges and all that sort of thing. So the first thing we're going to do is we're going to integrate. So if we look at the integral from negative L to L of f of x dx, this would equal, we can do termwise integration. So we get the integral of a0 over 2 dx plus the sum from n equals 1 to infinity. We can pull out the an and then just do the integral of the cosine n pi x over L dx plus bn integral of sine n pi x over L dx. But remember, we already computed a bunch of these cosine and sine integrals in the last video, and what we got was that sine of nx and cosine nx go away. They're 0 unless, except for the cosine 0 one. So for both of these terms, they're going to be 0 because our n is not 0, right? So n not equal to 0 here. And so even the cosine term is going to go away because of the oscillating nature of these integrands. So that means that we can get our a0 term, so I guess I should point that out. So this integral is just a constant. This is a0 over 2 times 2L, and then the 2's cancel. So what we get, we can actually solve for a0. We get a0 equals 1 over L times the integral from negative L to L of f of x dx. So if we have our function f of x and we can integrate it, then that tells us what our first coefficient is, a0. So integrating from negative L to L was a good trick for finding a0, but it killed off all the terms that had information about our other coefficients. So what we need now for the rest of the coefficients is a trick that's not going to kill off at least some of the integrals. So that trick is going to be multiplying by a special cosine or sine function and then integrating. So to find a m for m greater than or equal to 1, we're going to multiply by cosine m pi x over L, then integrate. So what we get is the integral from negative L to L, f of x cosine m pi x over L dx is a0 over 2 negative L to L cosine m pi x over L dx plus, let's do it this way, the sum from n equals 1 to infinity. We can pull out the an and then integrate negative L to L cosine n pi x over L cosine m pi x over L dx. And then our last one is going to be the b's. N equals 1 to infinity. We pull the b's out. And then we get a sine n pi x over L cosine m pi x over L. And now it suddenly becomes clear why we did all those integrals in the last video. And so let's pull up the results from that. Okay, so remember that m is not 0. It's greater than or equal to 1. So that means that this thing is going to get killed off, that integral. And then sine and cosine, whenever we have sine times cosine in any combination, that's going to equal 0. So that'll go away. And the cosine times cosine, we don't have to worry about this case because m and n are not equal 0. So now we only have to worry about that case. So this thing is going to be 0 unless m equals n. So now we can simplify this down to, we're only going to get when n equals m, so we have a m, and then that integral is just going to equal L. So that gives us a formula for our coefficient. AM is going to equal 1 over L, the integral from negative L to L of whatever you get when you multiply by f of x times cosine m pi x over L dx. So similarly, to find BM, we're going to multiply by sine of m pi x over L and integrate. And you should check that you can do sort of the same equations or this, the same computation that I did before, and we get this formula: BM equals 1 over L negative L to L of f of x times sine m pi x over L dx. So what we've done is said, if you can represent f by a power series, then we know what its coefficients would have to look like. So the last thing we're going to do in this video is to actually define a Fourier series, and then later on we'll worry about sort of when it's good. So definition, we're going to let f of x be a piecewise continuous function on negative L to L. And the reason that we're going to restrict ourselves to only thinking about piecewise continuous functions is that we need to be able to integrate f from negative L to L. And if it wasn't piecewise continuous, we wouldn't even be able to think about an integral. Okay. So then the Fourier series, I have no idea how well I'm pronouncing Fourier. If you listen to the Khan Academy videos, he says something more like Fourier. I'm not fluent in French. I don't have good French pronunciation, but I don't know. In my head, it's Fourier. So that's how I'm going to continue saying it. You can say it however you like, and I won't correct you. So anyway, the Fourier series of f is the trigonometric series. And I'm not going to write f of x equals. I'm just going to say it is associated with, or it is squiggly line. But we don't necessarily know that it's equal because we don't know anything about the convergence. But given an f, we can associate it with this series, a0 over 2 plus the sum of an cosine n pi x over L plus bn sine n pi x over L, where the an and bn are given by these formulas, the formulas that we just derived. An is 1 over L, integral from negative L to L, f of x cosine n pi x over L dx, and bn equals the same thing, but with sine. And that's for an is for n equals 0, 1, 2, etc. And the bn is only for 1, starting at 1. So that is the definition, and we're going to conclude the video there. We'll do some examples of this in lecture on whatever day we're talking about this, and you can also see them in the book. And then in the next video, the last video, I promise, on this section, we are going to talk about some of the convergence properties and other nice properties of the Fourier series.